Hello, my name is Farid Dinde bin Mubafiddin. Today I will present to you about the introduction for this presentation. For the first topic, I will tell about the spectral lines of hydrogen, which is the fifth topic in PHY310. Next, I will tell about the interstellar gas and dust in space. Spectral lines of hydrogen is the emission. The spectrum of hydrogen has been divided into a number of spectral series with wavelengths given by the Rydberg formula. These observed spectral lines are due to the electron-making transition between two energy levels in an atom. Next, I will talk about electronic transition in a hydrogen atom. In atom, each orbit has a specific energy. Electron closest to the nucleus are the lowest energy, while electron the farthest from the nucleus are the highest energy. So this is an example of electronic transition in hydrogen atom. The first is Lyman series, the second is Balmer series, and the last is Paschen series. The Lyman series is a hydrogen spectral series of transitions and resulting ultraviolet emission lines of the hydrogen atom as an electron goes from n equal to 2 to n equal to 1, which is the lowest energy level of the electron. We also can use this formula to find the wavelength. The Balmer series is a series of spectral emission lines of the hydrogen atom that result from electron transitions from higher levels down to the energy level with principal quantum number 2. We also can use this formula to determine the Balmer series wavelength. Paschen series are the series of lines in the spectrum of the hydrogen atom which corresponds to transitions between the state with principal quantum number n equal to 3 and successive higher states. We also can use this formula to determine the Paschen series of wavelength. Next, I will talk about energy absorbed and emit in a transition. At room temperature, all hydrogen is at ground, n equal to 1. When electron changes the level, it decreases the energy and the atom emits the photons. The photon is emitted with the electron moving from a higher energy level to a lower energy level. The energy of the photon is the exact energy that is lost by electron by moving it to the lower energy level. The energy absorbed in a transition when photon knock an electron from one energy level to a higher one. This continuous spectral light entering gas will merge the dark lines at the hydrogen absorption spectrum. This is energy emitted and energy absorbed formula, where is R equal to Rydberg constant 1.0974 times 10 to the power of 7, and F equal to integer of final energy level and I integer on initial energy level, EF upper state of energy and EI lower state of energy.
Hi, Assalamualaikum. My name is Izahana and I will continue to the next slide, which is the example of the spectral lines of hydrogen, that is interstellar gas and dust in space. First of all, the definition of interstellar gas and dust in space is most of the gas between stars in our galaxy and other galaxies is hydrogen and helium, which is dispersed at different densities between the stars. The gas ratios are comparable to those of the Sun. Star formation starts with interstellar gas as its raw material. In addition to highly ionized oxygen, nitrogen, carbon and silicon, interstellar plasma has also been found to contain carbon monoxide and hydroxyl molecule, CO and OH, which are probably leftovers from previous supernova. Tiny granules and carbon, iron and iron magnesium silicates make up the dust, which is dispersed between the stars in our galaxy and other galaxies at variable densities.
The interstellar medium. The space between stars is not a vacuum, but it is filled with gas and dust that produce some of the most beautiful pictures in astronomy. the emission lines. Emission nebula, aka H2 regions, because the halogen is mostly ionized, it is a very hot, up to 25,000 K star exceeds the hydrogen gas around it to produce an emission spectrum. These nebula usually look pink due to blending of different Balmer emissions lines. The Hubble Space Telescope (HST) has been a very useful tool for astronomers studying gas in another galaxy. One reason is that being above the atmosphere means improved image quality. Images no longer twinkle.
So we enter to the next subtopic, which is self-awareness on this chapter. First of all, how does the interstellar gas and dust affect visible light from stars? Secondly, why was the interstellar gas and dust so important to our solar system? Lastly, the advantages and disadvantages spectral lines in interstellar dust and gas. The figure shown flowchart how does the interstellar gas and dust can affect visible light from stars. By dust screens can block light at optical wavelength. This creates apparently empty areas of space with no stars in optical image. Sometimes light is not completely blocked. Dust absorbs and scatters blue light more than red light. Thus, mostly red light passes through it. Consequently, a star position behind the dust will look redder than it really is. This effect is called interstellar reddening. Since part of it is lost, a star will also look fainter than expected. This phenomenon is known as optical extinction. Next is, why was the interstellar gas and dust are important to our solar system? Because first, the dust around a star is critical to forming celestial objects around it. Dust around star contains elements such as carbon and iron, which can help form planetary system. When a star is in its forming disk, otherwise known as T-tail phase, it is ejecting extremely hot wine dominated by positively charged particles called protons and neutral helium atoms. Dust clumps become pebbles. Pebbles become larger rocks that grind together to expand. The presence of gas helps particles of solid material stick together. Some break apart, but others hold on. These are building blocks of planets, sometimes called planetesimals. Moving to the next slide, where the disk is colder, far enough from the star that water can freeze. Tiny fragments of ice hitch a ride with dust. The tip snowballs can amass into giant planetary cores. These colder regions also allow gas molecules to slow down enough to be drawn onto a planet. The gas giants of our solar system are thought to have formed in the warmer parts of the disk. Closer to the star, rocky planets begin to form. After the icy giant form, there's not a lot of gas left for the terrestrial planets to accrete. Planets that are rocky like Mercury, Venus, Earth and Mars may take tens of millions of years to form after the birth of the star. Once planets form around a star, they are referred to as planetary systems, which are defined as sets of gravitationally bound objects that orbit a star. Lastly, they can consist of one or more planets, but may also include dwarf planets, such as asteroids, natural satellites, meteors, and comets. The Sun and its planets, including the Earth, which is our planet, is known as the solar system. The term extrasolar system and exoplanet system refer to planetary system other than our planet. So, interstellar gas and dust is so important to our solar system. Thank you. Moving to the next subtopic on self-awareness, which is advantages and disadvantages conducting spectral lines in interstellar gas and dust. The advantages are, number one is the right temperature. Several molecules' rotational transition are excited, and when the excited states degrade, they produce a photon in a radio spectrum. Secondly, quantized electronic structure of an atom. The hydrogen spectrum is an important piece of evidence to reveal the quantized electronic structure of an atom. As soon as an electric discharge passes through a gaseous hydrogen molecule, the molecule's hydrogen atom disintegrates. However, there are also have a few disadvantages that this option must be costing when conducting it. The costing and operating expenses are too much and not affordable when we use this option. The fact is, the spectral line also limitation of hydrogen spectrum. It cannot predict the relative intensities of spectral lines. The other emissions lines either have wavelengths that are too long or too short that can be seen by the human eye.
Hello, so now I will present about issues related to interstellar gas and dust in space. Let's get started. First of all, supernova is stellar explosion. In easy term, supernova happens when binary star explodes and brighten up the sky. Through deeper term, supernova occurs when certain extremely big stars reach the end of their lives, explode, thus creating supernova. Supernova are incredibly uncommon thing to happen. A single supernova can briefly outshine an entire galaxy and emit more energy in a single second than the sun does in its entire lifetime. Additionally, they are the universe's main supplier of heavy materials. According to NASA, supernova are the greatest explosion that occurs in space. Researchers' best calculations indicate that such occurrences only take place once per 10,000 years in our galaxy, which is inside the globular clusters. Astronomers have only lately been able to witness such mergers taking place because to continual advancements in instrumentation and technology. No one has ever seen this phenomenon in action before, but that may soon change. According to study from a team of researchers from Kelvin College in Grand Rapids, a binary star system will probably unite and explode in 2022. This is a significant discovery because it will enable scientists to view the first ever star merger and explosion. Furthermore, they assert that observers on Earth will be able to see this explosion with their own eyes. This event is claimed that will cause an outburst of light so bright that it will become the brightest object in the night sky. So far, there are not any unwanted events that may occur due to the supernova. Even if there are any issues that happen during the explosion, it is only natural to happen. But because they are so strong, supernova produce brand new atomic nuclei. The shockwave is created when a large star collapse can trigger fusion reactions in the star's outer shell. Nucleosynthesis, a process that results from these fusion processes, produces fresh atomic nuclei. All that is left after a core collapse supernova is a dense core and hot gas known as a nebula. The center of stars that are particularly massive collapse into black holes. If not, the core develops into an incredibly dense neutron star.